In this session, we are discussing sequential circuits. Actually, the circuits are of two types. One is combinational logic circuits and another one is sequential circuits. Already in the previous sessions, we had discussed about the combinational logic circuits. Whereas in the combinational logic circuits, the output depends only on the current input. So it has no memory elements. But in the sequential logic circuits, the output depends not only on the current input but also on the past input values. For example, if we consider the design counter, suppose initially if the design counter value is equals to 000, so next time its value will be equals to 001. Suppose if the initial value is equals to 100, so the next value will be equals to 101. So always the output will be depends upon the previous value. So it needs some type of memory elements to remember the past input values. This is the block diagram of sequential circuits. So here we have to consider the combinational circuits. So the output of these combinational circuits can be stored in storage elements. So the present outputs, it depends upon the present inputs as well as the previous outputs. What is the concept behind the sequential logic? So the sequential logic circuits remember the past inputs as well as the past circuit state. State refers to the output. Outputs from the system are feedback as the input as the new inputs. The storage elements are the circuits that are capable of storing binary information, and these storage elements we can refer it as memory. Sequential circuits are of two types. One is synchronous sequential circuit and another one is asynchronous sequential circuit. Synchronous sequential circuit. The circuit output changes only at some discrete instance of time. This type of circuits achieves synchronization by using a timing signal called the clock pulse. So always the synchronous sequential circuit contains the clock signal. Whereas coming to the asynchronous sequential circuits, the circuit output can change only at any discrete time. So that means here we are not using any clock. So the basic and the major difference between the synchronous and asynchronous is the synchronous sequential circuit contains the clock signals and the asynchronous sequential circuit, it does not contain any clock signals. So first we'll discuss about synchronous sequential circuits. So the important synchronous sequential circuit is flip-flops, which can be used as state memories. So always the flip-flops can be used to store one memory element. So the flip-flops receives their inputs from the combinational circuit and also from a clock signal. With pulses that occur at fixed intervals of time, as shown in the timing diagram. So the smallest clock period is equals to the largest combinational circuit delay between any two directly connected flip-flops. So it is subjected to the impact of flip-flops setup time. So we will see one SR latch construction, and here the SR latch is implemented by using the NAND version. So the same SR latch can also be implemented by using the NOR gate, but we are limiting to our discussion to the NAND version of SR latch. So here the two NAND gates are cross coupled. So what do you mean by cross coupled? Cross coupled is nothing but the output of one gate can be the input for the another gate. So similarly, the output of this gate is the input for this gate. And here the inputs are S dash and R dash. And the outputs can be considered as Q and Q dash. So here first we are trying to write on the table for the different input combinations of S dash and R dash. So now we'll say that if these are the input values, what would be the values of Q and Q dash? Suppose if the S dash, R dash values are 0, 1. So before analyzing this particular output, just revise the concept of NAND gate. So within the NAND gate, when any one of the input is 0, the output is equals to 1. So if both the inputs are equals to 1, the output is equals to 0. So first we'll see that if S dash is equals to 0, R dash is equals to 1, what happens to the circuit? So we know that if any one of the input is 0, there is no need to check the other inputs. Directly we can say that the output value is equals to 1. So within these two inputs, so the first one, I mean S dash is equals to 0. So we can say that the Q value must be equals to 1, because if the input is 0, the output value is equals to 1. So here if the same 1 is applied to this NAND gate, so another input is already 1, and here the Q value is equals to 1. So 1, 1, it gives the value as 0. So if you apply S dash is equals to 0 and R dash is equals to 0, you are getting the output as 1, 0. And this particular condition is referred as set condition. So set means the output value will be equals to 1. So similarly, we'll see the next case. So here we are considering the next combination as 1, 1. So now S dash is equals to 1, R dash is equals to 1. So if one input is equals to 1, always the output value depends upon the another input. So if one input is 1, if the second input is 0, the output is equals to 1. If the second input is equals to 1, the output is equals to 0. Right. So here, if S dash is equals to 1, R dash is equals to 1, we will get the confusion which output we have to consider. So for that one, we have to consider the previous output. So here we know that the previous output or the previous state will be equals to 1 and 0. So then if you apply this 0 here, you will get the 1 0 combination, so that output value is equals to 1. And if you supply this 1 to this particular NAND gate, it gives the output as 0. So if you observe the two outputs, we can say that whatever the previous state is there, that can be maintained if the S dash is equals to 1 and R dash is equals to 1. And this condition we can refer it as hold condition. So similarly, we see the next case. So whereas in the next case, we are assuming that the S dash is equals to 1 and R dash is equals to 1. So if S dash is equals to 1 and R dash is equals to 0, it is very clear that here R dash is equals to 0. So as per the principle, you can say that the output is equals to 1. So Q dash is equals to 1. So this Q dash value can be applied to this NAND gate. So now these two values are 1 and 1. So for the 1, 1, the NAND gate output value will be equals to 0. So now the output will be 0, 1, which referred as reset condition. So if the Q value is equals to 1, it can said to be set condition. If the Q value is equals to 0, it's said to be the reset condition. So now we'll see that how this 1, 1 combination can hold the previous output. So here we are assuming that these two values are 0, 1. So then if the S dash is equals to 1 and R dash is equals to 1, what happens to the output? So if S dash and R dash again 1, 1 means always its values will be depends upon the second inputs. So here if you apply this Q, that is 0 value to this particular NAND gate, so 0, 1, it gives the output as. So if you give the 1 to this particular NAND gate, 1, 1, it gives the output as 0. So now the output value will be equals to 0, 1. So that means if the previous output is 0, 1, if you apply S dash equals to 1 and R dash equals to 1, we will get the value as same, that is 0, 1. So here if the S dash and R dash values are 0, 1, then set condition. If it is 1, 0, then it is reset condition. If it is 1, 1, we can say that it holds the previous state. So if it is 1, 0, it holds the same state. If it is 0, 1, it holds the same state. So now we'll see that what will happen if S dash is equals to 0 and R dash is equals to 0. If both the inputs are 0 or if any one of the input is 0, the output value is equals to 1. So here both at the Q output and at the Q dash output we are getting the values as 1, 1, which is not a correct or a defined state, because it can be defined as Q and it can be defined as Q dash. If it is 1, here you should get the 0. If it is 0, you should get the 1. But here in this case, we are getting both the values are equals to 1, which is a disallowed state. So this refers to the SR latch conditions. So mainly you should remember that what are the states we are getting by applying different values for this SR latch. So similarly, we can go through the SR latch with clock signal. So here to implement this particular circuit, so in the previous case we had considered the first input is S dash and another input is R dash. So here instead of supplying S dash and R dash, so we are supplying these S and R values through the clock signal, and again by using two more extra NAND gates. So here if the clock is equals to 0, so then we won't get any change in the output, so we can say that no change. If it is 1, then only you should go for the analysis of this circuit by using this S value and R value. So if it is 1, this particular circuit will be similar to our previous circuit. So 0, 0, it can be act as no change, 0, 1, reset state, 1, 0, set state, 1, 1, undefined state. So whereas how we had implemented the output in the previous case, so you can use the same thing and you can determine this particular truth table. So only the point you should remember that C equals to 1, then only this output can be determined. And the next one is the D latch, whereas the D latch can be referred as data transfer latch. So whatever the D value you are supplying, the same D value you will get as the output. So again the analysis procedure is same, so you can go through the same procedure. So here if C is equals to 0, we won't get any change in the output. If C is equals to 1, then only we have to check that what is the D value we are supplying. Right. So if C is equals to 1 and D is equals to 0, we will get the output value as 0. If C is equals to 1, D is equals to 1, we will get the output as equals to 1. So already I told that if the output is equals to 1, it can be considered as the set state. If the output is equals to 0, it can be considered as the reset state. And remember that this D latch can be worked as a data transfer flip-flop. So whatever the D value is there, that can be presented in the output. So in the next sessions, we will see some more topics related to the latches and flip-flops. So thanks for listening to class.